Hi everyone, welcome to meeting number 14 of the M2D2 series. We have the pleasure today to have Moksh with us. He will be presenting his work on epistemic uncertainty estimation for efficient search of drug. So before we start a bit about the speaker, Moksh is a graduate student at Milan and the University of Montreal, working under the supervision of Professor Joshua Bengio. He has his bachelor degree from Antique Surapkal. I'm sorry if I'm pronouncing that badly, sorry for that. He's interested in developing deep learning method for sequential decision making and the application for scientific discovery. Before joining Miller, he worked at Microsoft on research efficient machine learning methods. And it's a pleasure to have Moksh with us today. The floor is yours, Moksh. You can, yeah, how do you like to handle question? You can precise that and then jump into a talk.
Yeah. So, first of all, yeah, thank you for the invitation to speak here. It's a pleasure to speak here, and also thank you everyone for joining the talk. Just briefly about the questions. If you have any questions, please feel free to raise your hand so that we can take the question right away. Or if it is something you want to discuss in detail, please feel free to leave it in the chat. And towards the end, we will have some time to discuss questions, and we can take more detailed questions then. So yeah, so today I'll be talking about some of our recent work on epistemic uncertainty estimation in neural networks and how we can use it for improving the efficiency of search for novel candidates for drugs or several other applications. Um, yeah, so to begin with, let's talk about the process of scientific discovery in general. So we essentially have a very, let's say, imperfect model of the world, which we sort of rely on during during our day-to-day interactions with the world. Now, if we want to really discover or understand the real world, the process is generally follows this particular flow, right? So we come up with some interesting questions that we can ask about the world. Now, these can be very complicated questions, let's say, what are the laws governing how objects move or how objects interact? Or it can be something even much simpler than what's the time right now, or very basic questions. Now, we tend to form these questions into experiments that we can actually conduct in the real world. So, for example, to test the laws which govern the interaction of objects, we can actually see how two objects interact. We can have empirical evidence for that and so on. So we observe some results from the environment based on our experiments. So once you perform some experiment, we observe some result. And then finally, we sort of incorporate this knowledge to get a better model of the world. Right. Now we want to focus more on this particular question, which is where we believe deep learning and machine learning can sort of help us. So now, what are the sort of questions that we want to ask? So the questions that we want to ask can sort of be separated based on what our objective is in the end, right? So we can have two sorts of objectives. One would be we want to sort of obtain a better understanding of the world. So that that is more about let's say discovering laws governing the world, or how objects interact and so on. And the second one would be, how do we design objects with certain properties? So for example, let's say we don't really care that much about understanding the underlying dynamics of the world, but we just want to, let's say, get this one particular object which can sort of satisfy some properties which we are looking for. But just to note that these two are not necessarily mutually exclusive. So for example, you might not be able to design a better object without sort of knowing much about the world. So when we're trying to get a better model of the world, we want to sort of ask questions which will reveal something which we sort of previously did not know about the world, right? So um, uh, something which will reduce the uncertainty that we have about the nature of the world. Or in other words, you can say we want to maximize the information gain about the parameters of the world. So whatever parameters govern the world, we want to sort of maximize the information that we gain about them. Or the next one, which is probably more interesting for us, is how do we use this knowledge, or like how do, even without this knowledge, how do we sort of design new things which will sort of have certain properties. So here we don't necessarily want to just like rely on our like imperfect model of the world. We rather want to incorporate some limitations of what we do not know about the world, right? So we might like really just know about a very specific thing, but the knowledge doesn't really translate like to some other things which we do not know about. I'm being a bit abstract right now, but we'll make this a bit more concrete going forward. But yeah, so the goal here is we want to maximize the potential value rather than just try to find some like try to sort of base it on just our model of the world. So so yeah, now coming to the actual problem of drug discovery, right? So here the goal is we want to discover new drugs which can, let's say, inhibit a particular target, or inhibit a particular bacteria, or it can sort of bind to a particular target. And the main, really the key part here is we want to find something which is like already not been discovered, right? And it is satisfying certain criteria which we have. Um, so as you can see, like, so this is a very childish example for the drug discovery processes. We have a few molecules that we sort of, let's say, know about, and let's say the y-axis is some property of interest. So for example, let's say binding energy of with like binding affinity to a certain target ligand. We can see that like we do have like some information about this, let's say one of these maxima of this particular function, but we just don't have any information about this particular the other maxima of this property of interest. So the issue here is if we really just base our future experiments on this model itself, we would be missing out on this particular maxima, right? So ideally, we want something which is able to incorporate this potential value that we are missing out on. So more specifically, the reason why we might want to do this is also because when we are in, let's say, a drug discovery setting, like running these experiments is very expensive, and we need to rely on some computational methods to even suggest these candidates, because we can't really like directly optimize the wet lab experiments. So when we are sort of working with like some approximation of the world, we need to sort of think about how the model can go wrong. And more specifically, the message here is that like the models can be imperfect, but knowing where they are imperfect can help us in sort of guiding our discovery process and our search process. And like a very popular framework to sort of think about this problem is that of like sequential model based optimization. Now it encompasses like a lot of problems, and generally it's just a framework to model problems where you have like a sequential process of sort of generating and collecting data. And it sorry. So yeah, so the goal is essentially we want to sort of generate a data which can satisfy some particular criteria. So for example, it could be like maximizing a certain property and so on. But roughly it goes like this. So we start with some initial knowledge of the world, which is encoded in this data set D. And we can then we have this loop of, first we like have some policy which acts based on the knowledge of the world. So this could be generating new targets, right? And then we run this experiment in the real world. So we will have some observation, and then we can incorporate this new observations into our like existing data set, and we just repeat. So then the key part here is this part where we use the knowledge we already have to come up with new experiments. Now, a very popular instantiation of this framework is that of Bayesian optimization. So Bayesian optimization is just an instantiation of this sequential model-based optimization framework, where we rely on a Bayesian model for for generating the next candidates, and also sort of modeling the objective function that we're trying to maximize. So by the way, I won't be going a lot into detail about Bayesian optimization, but if you're interested, there was a fantastic talk at the M2D2 seminar by Aryan Deshwal, so you should definitely check that out. Now, so coming to the question of, like in Bayesian optimization, really what we rely on is we rely on the uncertainty estimates from this Bayesian model of our world. Now, so that brings us to the question, what really is uncertainty? So like, okay, going by the definition of Wikipedia, it's like a lack of it's a lack of certainty, or you can say a state of limited knowledge. So really what this means is that we lack some knowledge about the world, which sort of is, that's it. So it's just something which we lack about, like some information that we lack about the world. It's can be referred to as uncertainty. But more formally, we can really distinguish this uncertainty into two very fundamentally different quantities. So one is this, what we call the aleatoric uncertainty. So the aleatoric uncertainty is something which is a property of the environment, or like a property of the world that we live in. And it is something which is irreducible. So it's, let's say, you can think of it as something which is inevitable in the data collection process. So so there can be several things which leads to aleatoric uncertainty. So for example, if you consider some real world experiment, you can have the instruments which you use for measurement will have some amount of uncertainty associated to them, which is basically their error tolerance. So for example, if you are using a ruler, your ruler will have like marks of like 1 millimeter each. You just cannot, like, you physically cannot like go below that particular 1 millimeter threshold using the same instrument. So you can come up with like more and more powerful instruments, but at a point you reach some fundamental limits of the world, like the Heisenberg uncertainty principle. So at its core, like, there will always be some uncertainty in the world. Another instance to think about aleatoric uncertainty is, let's say, if you're thinking about some image classification task. Now, like image classification generally relies on humans who sort of label that particular image, right? So if we all agree on a particular label, then the label is set. But there can be instances where there can be disagreement among the human judges itself on what a particular image is. So that also is an instance of aleatoric uncertainty. So yeah, it is a property inherent to the environment. It is inherent to the data, and that's what is aleatoric uncertainty. But there is another aspect which depends really on the choice of our model, right? So this is the epistemic uncertainty. So the epistemic uncertainty is it's a consequence of having like finite data and finite modeling capacity. So really the idea here is like, if we had infinite data and infinite model capacity, so if we could sort of, let's say, learn all sorts of functions, and we had enough compute and data to sort of learn those functions, we could reduce the epistemic uncertainty. So it is something which goes to zero if we have, let's say, a perfect model of the world. So it is inherently tied to the model, or like how we choose to model the world. Or to make it a bit more concrete, let's consider this very simple example where we have these blue colored data, like these blue colored points, which form our data set. And as you can see, the points themselves are sort of like they are a noisy version of a sine wave, and like they're sort of separated by some distance. So this noise in the sine wave itself, so this is something which is irreducible, right? So these points themselves are observed with some Gaussian noise, for example. So they have some aleatoric uncertainty associated with them. But the other thing is, you have this model, which is the gray line. So this gray line is like the prediction of our model, and as you can see, like there is also some epistemic uncertainty associated, which is like, how wrong is my model? Like if I am, let's say, at -2. So yeah, so it is very important to think about these two distinctions of epistemic and aleatoric uncertainty, is because ideally we want to base our decisions on the epistemic uncertainty, which is like the lack of knowledge in our model, rather than aleatoric uncertainty, which is something we cannot really reduce. So which is why this distinction is important. Now, coming to epistemic uncertainty, focusing a bit more on epistemic uncertainty. So epistemic uncertainty is really like a consequence of having like there could like many possible functions which could fit your particular data set, right? So if you're trying to, let's say, learn this simple classifier between like squares, between triangles and circles, you can have like several, or in this case, infinitely many functions even within this particular model class, which can separate these two equally well. So this is what induces epistemic authority, and it also extends to like, if you like want to be a bit more flexible about it, you can have different model classes as well. So instead of just having a linear classifier, you can have these fancy classifiers. It essentially is really a consequence of having like several like possibly infinitely many predictors which can sort of have the similar performance on your data. So you can also think of it as like sort of a measure of the number of functions which can perfectly fit this particular data, right? Now there are several ways in which that people have sort of over the years come to represent what we call this epistemic uncertainty. So one of the popular ones is confidence intervals, but something more natural for people in machine learning would be something like the variance over the variance of like the posterior distribution over parameters, or the entropy of this distribution. So just to like briefly recap these concepts. So this is talking about like the probabilistic perspective on machine learning, where we have some prior over what the parameter, what the values of the parameter are. Then we observe some data which gives us the likelihood of that particular sample, and using the prior and the likelihood, we get a posterior, which is like an updated set of our beliefs over the value of the parameter. So this parameter so this is a very toy example. So this particular black curve indicates the posterior. So this posterior, we can compute things like a variance, which is the spread of this posterior. So like what is the sort of like how loosely spread is my belief over the parameter space, right? So that is a valid measure for uncertainty. And also another measure is the entropy, so which is like a standard information theory quantity. So really, like a lot of the work has been focused on these very broad characterizations of the epistemic uncertainty. Now, coming to everyone's favorite models, neural network. So neural networks, like if you traditionally think of them, they aren't necessarily very they aren't necessarily like out of the box able to produce uncertainties for their predictions. We really have to take the Bayesian perspective on neural networks. So essentially, what this means is like similar to the example which I showed previously. We have we have some posterior over the parameters of my neural network. So if you think about it, you have a set of weights. You just imagine those weights of your neural networks. They are sampled from from certain distribution, and that certain distribution phi is, so let's say your parameters are 5. We have a distribution over phi, and this posterior distribution is where the sort of weights are sampled from. Now, in order to estimate the uncertainty of my neural network, I can try to estimate this posterior. I can try to like find out, let's say, the variance of this posterior, and then use it as my uncertainty estimate. Now, if I really want to find this posterior, there are several methods to do that. So one is relying on local approximations. So I can, let's say, use a variational approximation to my posterior, which can make it easier to model, and then I can learn the posterior. Or I can use something like a Laplace approximation, or I can use some sampling based methods for sampling from this posterior. So for example, MCMC, Hamiltonian Monte Carlo, SGLD, and so on. So these are several methods for like broad methods for learning uncertainty estimates. But in practice, like a lot of these might not be feasible. For example, variational inference can have like poor approximations, and MCMC can be like hard to like model multimodal posteriors and so on. So in practice, there are like There are several approaches, but I just want to like focus on two of them. So the first and like the most popular and powerful one is the deep ensemble. And essentially what this is, it's an instance of like Bayesian model averaging. So you have different models of different models which have some stochasticity in them. So for example, you have a different random initialization, and you sort of uh, train these models on your data. And so this training on the data can also be sort of made more sort of sophisticated. So for example, you can train it only on certain fractions of like data which are for each of these different networks. And at the end, you just combine the predictions of these M models. So for example, if you want the uncertainty estimate, you will take the predictions of these M models, and you will just you can just output their variance as your epistemic uncertainty. And these work quite well in practice. So the deep ensembles, I should emphasize here, they are like state of the art, like in most settings. But they have this drawback of being computationally expensive, because you need to have like M different networks. The other popular baseline of choice which people use is what is called multicolor dropout. Essentially, what this relies on is like a Bayesian interpretation of the dropout function. So dropout, for people who are not familiar, is essentially a scheme where we drop certain weight connections within the neural network, and this can lead to like better regularization, so we can prevent overfitting. But there was also work which interpreted dropout as a form of a Bayesian approximation, and under certain conditions, you can say that networks with dropout would approximate certain Bayesian models. And people have used that to also estimate epistemic uncertainty. And essentially, what the process is, we sample different dropout masks and run the network with each of these dropout masks, and at the end, we average these predictions that we get. So this is also a pretty useful baseline, because this is very easy to implement. We really already have everything we want, and it works fairly well, I would say, but there are still some drawbacks which I will come to later. Okay, so before I move ahead, are there any questions like on things I covered so far?
I have a question. Can you hear me?
Yeah.
So in your, I think previous slide, you have equation. You have a P of phi given D. What's the phi here?
Yeah.
It's like a
So phi
parameter?
are parameters. Yeah.
Model parameter.
Yeah.
Oh, okay.
And D is the data set.
Okay. Yeah. Also, can you give a little bit of short description why this dropout or ensemble things is equivalent to the Bayesian uncertainty? Or
yeah, essentially the ensembles so there is a lot of disagreement within the community, but like one very intuitive explanation is you can think of ensembles as different, like, so for example, in a Gaussian process, you have like different you sample from a distribution over functions, and then you estimate like the variance in that distribution. Similarly, like you can think of deep ensembles as like an instantiation of that particular framework, where you are explicitly learning all those functions. So let's say you are allowed to fit like k different functions. So like intuitively, a disagreement among these k functions can tell you like how much more, like what you are missing. So going back to like my previous slides, I meant like I mentioned, like it can like the epistemic uncertainty can sort of be seen as a measure of like the number of different functions that you can fit, right? Or like the number of different functions which can fit the data equally well. So you can think of deep ensembles as just an instantiation of that particular idea, where you try to fit like k different networks, all starting from different initializations and sort of seeing the data differently, and then you can combine their predictions. So that will give, like, if you look at the disagreement in the prediction, that should tell you about the epistemic uncertainty. And dropout is also similar, although like you can think of it in a similar way, in the sense that if you have different dropout mask, it will give you sort of slightly different functions which can sort of fit the data. We can still fit the data. But there has also been work which says like standard dropout without certain conditions is not really Bayesian. So yeah, like the people like there is disagreement in the community of like what to call the actual Bayesian model or not. But I mean, for practical purposes, they do provide useful uncertainty estimates.
Okay. Okay. Thank you.
Yeah, thank you for the question. Any other questions?
There's a question in the chat by Chris, but I think it's answered by Joshua. If not,
Okay.
like Chris, you can open your mic and ask him.
Thank you. Joshua answered it, but I have another follow-up question. Is there a difference in the uncertainty estimation when they're using different architectures versus the same architecture?
Yes. So like the uncertainty estimates you will get are different, certainly. So it really depends on what it sort of clarifies what types. So it really depends on how different the architectures are. Let's say, for example, if you try to model some, let's say one thing, like one of your models is a neural network and another one of your model is, let's say, a linear regression. So both of these will learn very different functions. And in some cases it can be useful to have these different functions to sort of measure like what different model classes can sort of approximate this, like, or can fit this data well. You can in some instances get better uncertainty estimates if you have like different architectures, but it really depends.
Thank you.
Okay, so yeah, I'll move on. If you have any questions, please feel free to leave them in the chat and we can get back to them. So yeah, now before I talk about like our method for epistemic uncertainty estimation, I will sort of highlight the importance of uncertainty estimates in a very practical scenario. So we recently had some work on designing antimicrobial peptides, using some of our other recent work on GFlow. But generally, so the idea here was that you have a drug in the drug discovery process. You have like a series of long and different steps, which can be very expensive, which can take a lot of time, and so on. And more importantly, from like a modeling perspective, each of them will have a different accuracy and or like different fidelity, to be more precise, of the true property that you're trying to sort of understand or like sort of model. And they might also have certain other objectives which are added. So for example, in the in silico screening, we might just look at, let's say, a very, like for example, if you're trying to find molecules which bind to a particular target, in the in silico stage, you can use some very crude like docking programs, which are a very rough approximation. They're not exactly the same as, like, let's say, for example, what you would see in an actual experiment. So in the next stage, we will have some actual wet lab experiments where the fidelity of the docking energy would be increased. But then in the there will be, in the next stage, when we go to animal trials, you might have an additional objective of like the particular molecule which you propose not being toxic. As you can see, like there is a series of like different steps where in each step you might have something which is more precise, or something which is might be contradictory to what you saw before. So it is very important in the initial stages, let's say for example the in silico screening, which we focus more on, to generate a diverse set of candidates. So if we what diverse candidates would ensure is that even if you keep adding different properties, or if if the sort of approximation that you're trying to optimize is not really perfect, or it's like very bad, you still have like, you cover all its modes. Then you will if you cover all its modes, then you will like be at least guaranteed to satisfy that property. And in the future, like even if your set like keeps getting smaller and smaller and smaller, you might end up with something which is actually successful. I will not really go a lot into detail about the method here, but just to sort of like lay it out here, we have this very famous loop, inner loop and outer loop. So the inner loop is essentially here where we train our generator. So this generator is what something called a GFlowNet, which again I do not have time to cover in like any precise detail, but I have put some links to relevant talks and relevant articles which might be helpful for people who are interested in it. So we train this GFlowNet generator using a particular using this proxy, which is which is an approximation of the value of the actual oracle that we're interested in. and we have a data set of like evaluations of this oracle. The key aspect of the GFlowNet is that it can sample objects proportional to their reward rather than like sort of just maximizing them. So this is very important from the diversity perspective, which I mentioned earlier. But the key aspect here is, so in this particular work, we incorporated the uncertainty of this proxy in the reward function for the GFlowNet. So rather than using just the value or the prediction of the model, we also incorporate the uncertainty about the about that prediction using something called acquisition functions. So acquisition functions are really just you can think of them as heuristics of how to combine your prediction with your uncertainty estimation. Yeah, really it can be anything. So for example, upper confidence bound, where you just add your uncertainty estimates and that gives you like a let's say what is the maximum potential value I can get from this particular data point. Yeah, so the main idea here was that incorporating the information about uncertainty can help us sort of improve the search efficiency, because we know where to search, because what are the places where I'm lacking knowledge, and also like knowing the prediction value itself, you can make a case for like the potential value of that particular point. Yeah, so just to give some results, the metrics here we look at are performance, which is like the property of interest, which in this case was the antimicrobial activity, and the diversity is really just the distance between the generated sequences, and novelty, which is like how different is are the generated sequences from the known sequences. And as you can see, the GFlowNet based method works much better than prior work on all the three metrics. And more relevant to the talk here is that is the effect of uncertainty estimates. So as you can see, without uncertainty estimates, the results are not as impressive. And uncertainty estimates help sort of improve the results quite a lot. So they do improve efficiency and like sort of help us achieve state-of-the-art performance. Okay, so now I told you a lot about how these epistemic uncertainty methods are useful and like why they are great and why you should use them. Now I want to detail certain problems with the current methods. So the first one of them is most or like a lot of uncertainty estimation methods currently in use can have poor calibration of outer distribution data. Now, this is very important since in this like drug discovery setting, we really want to know our uncertainty on points which are out of distribution, because like that, those are the points which we really want to acquire. If we don't want to acquire something which is already known to us. So this is a sort of very important problem for the drug discovery context. So, and like this is a very simple example is illustrating it. So let's say we have a Gaussian process which is fit on this data. So the blue points are my initial data set. Let's say then I add a point at 0.7 in the training data of the GP. It is still estimating very low uncertainty in this region, even though like it has like seen nothing here, right? So we would expect it to have like fairly high uncertainty estimates in this particular region. And this other figure that is taken from our paper, we see this, we see the overestimation and underestimation of the uncertainty estimates. So as you can see, so this is from an ensemble. You can see the uncertainty is like many times overestimated, underestimated. So it's not very accurate on OOD data. And the second one, which is also like really important from a more machine learning perspective, is the effect of model misspecification. So like something which I didn't really touch upon a lot, but as I mentioned earlier, like it really depends, like the posterior of your the posterior over parameters, it really depends on the prior you have in mind. So if your prior is, let's say, misspecified, so what this means is, let's say you're trying to model like a non-linear problem with a linear classifier, your linear classifier would not have enough, would not be like of the main model class, but your uncertainty estimates will not account for the fact that you are in the wrong model class. So the effect of model misspecification can be very problematic for uncertainty estimation and even like generalization when you train like Bayesian models. And it has been shown to have like suboptimal suboptimal behavior. More specifically, so if you look at this figure, let's say this orange surface is the method, is the function class that you're looking at, and let's say this f tilde is the is the sort of closest predictor within this model class to our actual predictor, which is f star, and let's say f hat is the learned predictor. So what traditional Bayesian methods would measure is this distance essentially in function space. Whereas what we really care about is this distance of like the function from the true function. So essentially what it misses is this bias. And like I mentioned earlier, there are also some other problems, including like poor approximation for variational methods. There can be mode mixing issues with MCMC methods, and also, for example, Hamiltonian Monte Carlo can be computationally very expensive and not very feasible. Yeah, so now finally coming to, I guess, the star of the talk is DEUP. So the main idea here was, what if we just try to estimate, what if we characterize the uncertainty estimate instead of as, let's say, the variance over my posterior, which misses out on the effect of model misspecification. How about I really just reinterpret what uncertainty is as, let's say, my estimate of my generalization error, right? So if I if you look at a predictor, like if the predictor can, let's say, have an estimate of, let's say, how far it is from the from the true value of that particular point, that can be a useful estimate of uncertainty, because you know, okay, I'm this much far, I need to sort of go there and like see if I'm really accurate there. And a higher uncertainty would also indicate like poor approximation quality. So we really felt this might be a good fit for situations with like situations involving sequential decision making. And roughly, the idea is we have a main predictor. This is our standard machine learning method. So it can be a regressor, classifier, whatever. And we augment it with this additional error predictor, which will try to predict this out of distribution error for this for the data points. Now, it is key to note that this error predictor is also trained on out of distribution points, which is why it is sort of able to generalize out of distribution. Otherwise, like if you just train it on points already on the training data, you cannot expect it to generalize out of distribution just looking at everything inside the training data and sort of expecting it to predict like the loss out of distribution accurately. And I will get to how, like, what is needed to actually achieve this. Yeah, so let's get started. So before moving ahead, we sort of lay out our definition for what this uncertainty really is in like mathematical terms. So we refer to the total uncertainty as the loss of our predictor. So like the total uncertainty is essentially just the loss that we have for a particular predictor. The next thing is the aleatoric uncertainty. So what we define as aleatoric uncertainty is the error made by the Bayes optimal predictor. So Bayes optimal predictor, you can just think about it as the predictor which has infinite compute and infinite data. So given infinite data and infinite compute, if I am able to sort of learn a predictor, what is the error that predictor will make? So essentially, it's just like the noise in the environment. So yeah, so the the aleatoric uncertainty is the total uncertainty of Bayes optimal predictor. The epistemic uncertainty, then we define it as the reducible part of the loss. So if I have a total uncertainty and I take away the aleatoric uncertainty out of it, whatever is left is my epistemic uncertainty. So it is essentially the part of the uncertainty which I can actually reduce by looking at more data and, let's say, having more capacity. So we have in the paper we have this proposition which talks about how this particular situation is valid in case of regression. We also have a proof of how this is valid in the case of classification settings, where you have like a negative law likelihood loss, and here it is a mean squared error loss. But really, you can think of it as when we characterize our epistemic uncertainty in terms of the in terms of the reducible part of the loss, it really models this particular quantity which I alluded to earlier, of the error between of really like the distance between your learned predictor and your true underlying or like true underlying function. Sorry. Um, yeah. So now that I have a definition of the uncertainty, I can I can sort of come up with an algorithm to estimate it, right? So really like it is a very simple to understand algorithm. So we have some normal machine learning, right? So we first have our data set. We have some out of distribution samples for X and Y. I will get to like how we get these out of distribution samples a bit after this slide. But let's say we have some out of distribution examples and we have some training examples. And we sort of have these predictors. We first will do standard machine learning. We fit our predictor on our data set. So we'll only fit it on the training data set, not on the out of sample predictions. Then in our we'll also fit features in 5D. So I will come to these features again a bit later. But then we use the out of sample we take this out of sample data set which we have, and I will evaluate the error of my predictor on all these out of sample points. So this will give me an sort of expanded data set DE, and I will also evaluate my function at the in distribution data points so that we also know about what the in distribution error is. And I will simply fit an estimator E on the total on this combined data set. So this estimator will learn how to predict the error. Now, one thing which I assume here is we have an estimator of aleatoric uncertainty. Now, this estimator, it is also possible to estimate it from data if you have access to the Oracle. But for now, let's just assume that we have like a trained estimator, or like I know what the aleatoric uncertainty is, so I can just subtract it. So basically, for getting the epistemic uncertainty at any point X, all I really need to do is I estimate the error using my error predictor, and I remove the aleatoric uncertainty from it. And this will give me the epistemic uncertainty. So it really is like a very straightforward procedure if you look at it. Now, coming to the like very obvious question of like how do we deal with out of distribution points? So like I mentioned earlier, this is very like this method was really focused on like interactive, like sequential decision making settings. So in sequential decision making settings that I talked about earlier, you have this loop where you sort of generate new data, then you sort of get and then you sort of observe the actual value of that data, and then you incorporate it in your data set and so on. So there are 2 points here. One is before we sort of incorporate the data in my policy, which is basically my function, that point is out of distribution, right? Like before my predictor is trained on that particular data point, that point is out of distribution for my predictor. And once I have trained my predictor with it, it becomes in distribution. So really for each data point, I can have 2 training examples for my uncertainty estimator. One would be where it was out of sample, and one is where it was in sample, right? So before we train the main predictor on it, and after we train the main predictor on it, there will be 2 points which we can sort of use as clues for the error estimator. So if I give my error estimator a point before the data set, before it is trained on the main predictor, and tell it that, okay, yeah, this has not yet been seen by the main predictor. You can, and I also give it like after it has been trained with the main predictor, you can expect your error predictor to get some clues of like what out of distribution point looks like and what in distribution points look like. So that is one of really like the key aspect which makes DEUP work and work well in sequential settings. Now, but if you think about it, like it introduces a lot of non-stationarity, right? So if you think about it, if I'm just estimating, if I'm learning a predictor to estimate the loss of a model, it can't be very accurate because the loss of the predictor keeps going down, right? So the loss of the predictor keeps changing. The loss of the as I see more and more data points, like my loss at each data point in my state space will change, and it might go lower. We expect it to go lower, or it can also go higher. But like it's really induces this non-stationarity. So to deal with this non-stationarity, we propose using what we call stationarizing features. So stationarizing features are essentially just features which can help give the error predictor some clues on estimating the true uncertainty. So, okay, consider, for example, this data set called 2 moons. So we have this data points highlighted in purple, right? Now, if I, let's say, have an estimator of, if I have, let's say, a density estimator fit on this data set, it would look something like this, let's say. Now, if you look at this density estimate, you can sort of learn a lot about a particular point and what its generalization error might be looking at the density estimate. So for example, if I look at the density estimate on the data set, like, so let's say in this one of these yellow regions, my density estimates will be very, density estimator will have like a very high output. What this will indicate to me is that the point is in distribution. It will tell me something about the distribution of data that I've seen, or like the data set that I've seen, and this new point of interest. And this distance can tell me a lot about what my generalization error should be. So I would expect a higher generalization for like a higher density, or sorry, for a lower density for a point which is further away from the training data. So the density can be a useful clue. And the next one is variance. So I mentioned earlier that the posterior variance is not a sufficient proxy for epistemic uncertainty, but it is still a good proxy. Is what I want to highlight here. Is if you look at the uncertainty estimates, so in this particular figure, the yellow part is essentially the uncertainty estimate from a Gaussian process, which is a Bayesian model, non-parametric model. And if you look at it, except for the data set, the variance everywhere else is quite high. So if I don't have access to, let's say, a density estimator, if I have a variance estimator, or let's say, for example, I can get this variance even from MC dropout, which won't be a good, like a particularly great variance estimate, but it will still be useful. So yeah, these features can give me clues, and in fact, we can use any estimate to like any previous work, let's say called from like Gaussian processes and like MC dropout to various other methods that people have proposed. We can in fact use those as input to our error predictor and improve like the quality of uncertainty estimates. So this is like you can sort of guarantee it to be better than like any other method of interest, and be more accurate about the quantity that we really care about of this epistemic uncertainty. Now, just to like briefly share some results that we have. These are already in the paper, which you can refer to. So one of our experiments focused on estimating the uncertainty over combinations of drugs. And I think like I can't do a better job than Paul did last week at his MP2 talk on this particular topic. So please feel free to check it out. But yeah, so but really like what we observe is that we get extremely strong uncertainty estimates from DEUP over existing methods. The next task, which might be more familiar to people in machine learning, is that of identifying out of distribution inputs. So let's say I have a predictor which is trained on the CFAR10 dataset, and I want to use it to sort of identify if I give it an input from some other data set, SVHN, which is out of distribution. So I guess the rough idea here is we want to know when the model does not know, right? So if the model sees something which is out of distribution, it should predict a high uncertainty estimate, which should tell us that, okay, maybe we should not rely on the prediction of the model. So this is a very standard setup that people have proposed. So we train on these CFAR10 images, which is like planes and cars and so on, and then we try to test it on SVHN, which is really images of like house numbers and so on. And what we expect is the uncertainty on these out of distribution points should be higher. So we should be able to accurately distinguish between the points that we have seen and the points that we have not seen. And here we see like DEUP outperforms all the previous methods in terms of these two metrics. So just to talk a bit more about these two metrics. So this is the Spearman rank correlation. So essentially, how well are my uncertainty estimates correlated to the actual generalization error of my predictor? And the AUROC is like a standard metric which people use for, so let's say if I am making the prediction of higher uncertainty prediction on a particular example and sort of classifying it as out of distribution. So what is the area AUC for that particular classification? Next and more interesting from like the sequential model optimization view is our results on sequential model optimization. So this is one of the simple examples that I chose from the paper, but there are several other examples. So as you can see, this function has like a lot of maxima. So the goal here is we want to find the maximum point, which would be at like 1.8. We use the standard framework of Bayesian optimization, and we want to find this maximum point. We really just took the DEUP uncertainty estimates and fed it to like a standard and like sort of replaced the Gaussian process in like a standard BO framework, and it like works extremely well. So I mean, this is a very simple toy example, but we have results on like some more complicated examples as well. It is sort of the only method which can actually reach the maximum. The next one, and I guess I didn't really touch a lot on this, but reinforcement learning can benefit a lot from useful uncertainty estimates. So it can help us do efficient exploration. So if we have uncertainty in the parameters of our uncertainty over the parameters of our, let's say, value function or for a policy, we can use that as a sort of signal for guiding exploration. So in this particular set of experiments, we use the uncertainty estimates as the exploration bonus. So essentially, if a particular if our agent visits a particular state which is sort of is new to or it's uncertain about, then it gets this bonus which is equal to like our uncertainty estimate. And what we observe is that it works quite well on the tasks that we tested. And it actually achieves the lowest regret, it even better than like sort of methods which have been designed for exploration in reinforcement learning. So I think just to like give a brief conclusion to all that I've discussed before. So epistemic uncertainty is a powerful signal, and I guess this is not something which we discovered. It's like sort of a known thing. But what is more interesting is if we can interpret the uncertainty estimates as like an estimate of generalization error, it can help us mitigate the issues that existing methods can have in terms of, for example, model misspecification. But just to highlight, one important aspect is that like while sort of DEUP seemed very simple in like principle and in explanation, like instrumenting it in an active learning setting can be somewhat challenging in terms of compute and also like complexity of actually implementing it within your existing framework. But I think there is lots of potential for future work to like make it more efficient. We can sort of combine a lot of the features that we learn, stationary features, with the main predictor and so on. But yeah, there's a lot of potential for future work there. And another also very important aspect is the biological validation, like actual wet lab validations for some of the results that we presented, because I mean, it's easy for like as machine learning scientists to claim that, okay, this method should work and so on. But unless we have some actual experimental validation, it is still something like which we need to claim that. So that's it. I just want to thank all of my co-authors and like lots of groups at Mila who have been instrumental in discussions relating to both of these projects that I discussed today, and also to people who have supported the research financially. Yeah, and now I'm open to questions.
Thank you much for the excellent presentation. Yeah, also for people who haven't been following the chat, there has been already some interesting conversation going on there, so please take a look. For question, I'm can start with the first one. So you use a kind of a definition of outer distribution generalization that I would say for me is a bit incomplete in the sense that, for example, if you take proteins or like peptides or molecule, you cannot just define outer distribution as what's coming in the next batch of experiments, right? Because like this next batch of experiments might have some molecular peptides that are very similar to the ones that we have in the training set, and some that are very far from that training set. So yeah, just want to have your thought on on that particular thing.
Yeah, so just to be clear, like we don't necessarily mean that like the next batch has to necessarily be like out of distribution very far from the training set and so on. So really the point here is when we sort of are in these acquisition settings, the next even though the next batch might have some of the examples which are very similar to things that we have already seen, it will have some examples which can be very different from what you have seen before, and you can rely on like those examples to sort of build, like even if it's a small, if it's some information about out of distribution points. So really the goal is here is like we want to look at these batches that we acquire, and from these batches we can sort of infer something about like the distribution that we do not already know, and like what the loss might be on these out of distribution points, which, or like what the error our predictor might make on points which are like very far away, and that should give us a useful signal to like be able to predict it, like, and maybe extrapolate it outside of the training distribution that we see.
Maybe I can add another point, which is that you have to remember that the the epistemic uncertainty prediction that we're doing with DEUP is conditioned on the input. So depending on, say, the molecule, it could predict a different level of uncertainty, right? So the easy molecules that look like the ones you've seen before, it's going to learn that they look like the things I've seen before, so I don't expect a lot of error. The things that are very new, they're far from things you've learned before, is going to predict there's going to high level of error. So these two things are not like hurting, there's no approximation that is being violated here by having a mix of easy and hard out of sample examples, or far out of distribution versus close to the original distribution.
Thank you, Yoshua, for the clarification. Thank you much. One other point I'd like to bring here is the number of what's actually is there any number of OOD sample that you need to see to better estimate the epistemic uncertainty?
Yeah, that's a good question. So we don't really have any like sample complexity sort of bounds on like how many samples out of distribution do I need to see in order to sort of be able to generalize well out of distribution. So yeah, we don't have any, like, at least theoretically, any such results, but more practically, I think it really depends also from like the domain to domain. So in certain, for example, toy domains of sequential model optimization, you might be okay if you, even if you see like, let's say only a fraction, let's say 0.1 or 0.1%, or sorry, 1% of the examples that you have acquired are out of distribution. But yeah, I don't really, unfortunately, I don't have any concrete answer to that question. Like, it really depends a lot.
Okay, thank you. Any more question? That's all for me.
So okay, there was a question in the chat for the last figure. For MC dropout DQN being worse than DQN plus epsilon VD. Yeah, so actually, like, yeah, that's a very good question. So we were also initially somewhat surprised by like the order of the regret of these methods, and like the sort of best explanation that we have so far. We haven't probed into it for a lot, but the best explanation we have so far is that this like the MC dropout, so the epsilon greedy DQN is sort of guaranteed to explore like all parts of the state space, because you will make the epsilon, you will take like random actions with the probability epsilon. Whereas in the MC dropout DQN, you really just rely on this uncertainty or the bonus of this uncertainty from MC dropout. So it is not guaranteed to sort of explore your entire state space. So we believe that that might be what is causing this parent discrepancy. Does that answer your question? Okay, thank you.
Any more questions?
I see there is also a question, like there's a lot of discussion on uncertainty, like benchmarks and so on. So like just to point out, like there is like sort of large scale effort for like studying the effect of like uncertainty estimates calibration called uncertainty baselines, released by Google and the Jain group at Oxford, which might be of interest to people looking for like a more comprehensive empirical evaluation. But the only sort of shortcoming is the uncertainty baseline as of now focuses only on like sort of static data set settings. So for example, you have they for example have experiments similar to those of our like these CFAR and SVHN experiments. So yeah, it is like an excellent benchmark, but it doesn't cover like sequential settings.
Cool. Thank you so much for the for answering all those questions and for the great presentation. There's one question, sorry. Go ahead, please.
Yeah, I just had one quick question. So apart from the variational approximation method, the MC dropout, the rest of the NN-based method that you have tried, are those scalable to large data sets?
Yes, so actually there has been a like bunch of recent work on like sort of single pass methods for uncertainty estimation. So for example, these data sets like DUE and these methods like DUE and DUQ, they rely on like a single forward pass of a neural network to estimate uncertainty. So it's like much cheaper than running, let's say, an ensemble or even MC dropout. So they tend to scale fairly well. I've seen experiments of people running them on things like ImageNet and so on. So yeah, like there are definitely alternatives which work quite well on a large scale. And just to be clear, like we can even instrument DEUP to work on them. But my comment at the end was just that it is since we have these different aspects to take care of, like having different features, so we have to train different networks with different loss functions, for example. So it's a bit of like it's not very trivial to integrate it in, let's say, something which you might have already existing compared to other methods.
I mean, you chose the GP as a baseline in the Bayesian optimization framework, which definitely it's not scalable because it's cubic in terms of sample complexity. Yeah. So that's why I was wondering, there's been recent literature on conditional neural processes in which they combine GPs in a neural network framework, which is, I think, linearly scalable. But then I think the rest of the deep learning methods are definitely very interesting. Thanks a lot.
Yeah. Yeah, thank you for the question.
Okay, great. So I think we can stop here if there's no more question. Thank you again much for the great presentation, and thank you all for attending this talk. There is a link to our Slack channel to join there in the chat. Please consider joining if you want to have more questions for Moksh. He's on the Slack channel and we'll be happy to answer those. If nothing more to discuss, happy to see everyone next week, where we're talking about graph neural network in drug discovery presented by DEUP, meaning Bayani. Thank you, everyone, and have a good day.